Thank you. So a software engineer builds an OpenPOWER Core in Chisel. Oh, what could go wrong? Spoiler alert, quite a lot. But before we get there, I'd like to just give you a bit of background on why I'm here. Has anyone heard the Power Architecture before? Hopefully, PowerPC, yes. We've been around a while, many decades. I work kind of in a different world. I'm mostly a software engineer. We do servers. Some of the most recent things our broad team have done is Summit and Sierra, the number 1 and number 2 supercomputers currently in the world. And a number of years ago, we created something called the OpenPOWER Foundation. And this was more around open hardware in terms of system design, so open board designs and all that kind of stuff. As part of that work, the Firmware Stack that we run, and in fact the same Firmware Stack here runs on the 2 supercomputers, is completely open source. So from first instruction right through to booting Linux, it's all open source software. You can get it on GitHub. If you want to build it and run it, you can with some of our partner boxes. One of our partner boxes, this is a Power 9-based workstation. It's, again, completely open source. Raptor, their business is in owner control computing, so everything on it is open hardware, open source software. You can get the board schematics, the whole lot. A couple of months ago, we announced that the PowerPC architecture, the Power architecture, was now open. That was back in August. And there are a few things we did there. Firstly, the instruction set is open. PowerPC, PowerPC 64, it's all the same thing. Basically now the architecture is called Power. It's royalty free, it includes a patent grant. The OpenPOWER Foundation now moves under the Linux Foundation. And we did one more thing. We announced a reference design. We called it MicroWatt. And this is a very simple 64-bit core. It's using what we call the OpenICE Scala fixed point subset. Written in VHDL 2008, uses all open source tools for synthesis and design. And we released that in August. But that's VHDL. What does that have to do with Chisel? Absolutely nothing. What we did next was we just thought we'd go back and build another core. So in the last couple of months, I've been working to build a Chisel core, and so we put it up on GitHub as of this morning. It's functional. It's simple, 2,000 lines of Chisel, hardly anything, hopefully easy to for anyone to understand. It uses Chisel tests, so Scala's been helping me along, so hopefully I'm using some of the newer interfaces coming out, so thank you, Richard, for that. It's targeted at FPGAs, so the way we work and we play with this stuff is all on open FPGA toolchains. So we're using Yosis and NextPNR, which are some very powerful open source synthesis tools. And as I said, as of this morning, it's up on GitHub, so you can pull it, you can play with it, you can build it, simulate it on Verilator, or synthesize it on an FPGA. In terms of language support, what do we support today on this little Chisel core? Well, one of the advantages we have is that the Power architecture has been around quite a long while. So we have a number of tools that work. All my development, I just use standard distro toolchains. So if I'm working on my Raptor box, I just use the native toolchain. If I'm cross-compiling on my laptop, I use the standard cross-compiling tools that are available on distros. So what works today? Well, C works. Well, that's pretty boring. You know, that's something at least. That's a start. We have MicroPison going. Anyone play with MicroPison? It's a cool little tiny Python interpreter you can pretty much put on anything. So that runs on top of the core. One of our people back home wasn't happy with this, and so they ported Forth to it. I don't know why, but we support Forth. Fantastic. And there's a few other things on our other core. We support Rust. I just need to add a few more instructions. We should have Rust support in a couple of days, I hope. We talked about synthesis, and this is one of my favorite little boards. This is actually an ECP5. There's a maker in Adelaide in Australia, Greg Davil, and he builds cool little bits of technology. So he's built a feather form factor ECP5 board, and we've been playing with it, and we're using Yosis and NextPNR to put our core on top of it. One of the things we use is we're using Docker containers, so it's very easy to get involved. You don't need to actually build a lot of these tools. So Yosis and NextPNR come to you via a Docker container. And the interesting thing was, and I found quite exciting, is at least on the Chisel side, it took me about 30 minutes to go from a working core in Verilator to getting it on this FPGA. So it worked in simulation, and it did actually just work on the FPGA. So I thought that was pretty fantastic. So let's talk a bit about Chisel. My background, systems programming. I'm kind of a recovering Linux kernel developer. C, assembly is what I do. So there were a series of steps I needed to do to kind of get up to speed. Firstly, I hadn't done much functional programming before, so there was the Scala hump, and I kind of had to get over that. I did really enjoy it in the end, and the last couple of weeks of work have been fantastic. But it took me a few humps, and my secret weapon here was Scala. So anytime I had a problem and I got frustrated, I was about to throw everything away, he'd come forward and say, no, you're thinking about it wrong, and this is how we should do it. So that was really, really useful. First thing I point out is the thing that annoyed me the first was build times, because from my perspective, I like to iterate fast. If it's more than 5 seconds, I've switched out, I'm looking at Twitter, I'm looking at the news, I'm responding to Slack, something like that, and then you eventually come back in. And so I'm really, really excited to see someone's added mill support. I haven't worked out how to use it yet. Maybe we need a Chisel template so I can just copy that. But getting it down at 8 seconds is great. It'd be great to get it even shorter. So perhaps we could have -0, just build it. I don't care about optimizations. Just tell me if I'm good or I'm not. And then eventually you can add optimizations, that kind of stuff. So getting that cycle, that closed loop cycle around to a couple seconds would be fantastic, I think. Error messages, I'm sure we've all been here, but every time you get an error message and it keeps going and we're not done yet, and then you finally have to work out what's going wrong, and I kind of sigh every time I see it, and it's getting better, but every time you get an error message like that, you think, oh gosh, what have I done wrong? Enums, the standard enums, there's not much to them, there's no safety, kind of surprised me, it's even worse than VHDL. Strong enums are coming, great. We need more examples. Maybe new developers can get straight on them, because I missed that boat. I got to go back and work out what they are and make it happen. So I think publicising them some more and all the examples using the best of the best in terms of language would be a good idea. Verilated warnings. As a software person, I like to wall the world, enable all warnings and everything, and so I did. And I started getting errors, not errors, but warnings all over the place. And there was some in some of this boilerplate code that Scala was just talking about. And why? Well, no real reason. We can probably fix it. But cleaning this stuff up and coming from the Linux kernel world where no warnings, 0 warnings. You introduce a warning, you fix it. And I'd love to get my projects to that level, but there's a bunch of stuff that I have to fix or has to be fixed in the tools before I can get there. Similarly, Scala warnings, you turn on a bunch of Scala flags, which you might want to do, and then all of a sudden you start getting a bunch more warnings. And this was one example where you have nested else whens and else whens, and all of a sudden you get a whole bunch of these warnings. And it turns out it's fixable. Scala fixed it, fantastic. And so they go away, and then my warnings now shrink down to a whole bunch less. So my aim is basically to have all the warnings on, not get any warnings, and then in the CI flag every time someone adds a warning, fail at commit, and then someone can come and fix it. The other thing, I'm not really sure. I like to look at every single module, play with it, look how it optimizes, maybe look at an Fmax for this, all that kind of stuff. I end up putting, boilerplate at the bottom of every file. Maybe that's right, I don't know. But, I haven't kind of found any other easy way just to build little bits and pieces. So I don't think that's me. Some of the oddities, people have talked about things like partial assignment. Coming from my couple months of VHDL, that was my first pain. I think I'm over it now, but that was a bit painful for the time. And on the other hand, people were talking about how you can truncate. Yeah, okay, I agree. Let's get something like Chisel 3 strict going and start fixing up some of these things. And I'm happy, at least in my project, to kind of follow along with that and then apply best practices as time goes on. Memories, I've only just started getting into it. I got a couple of bug reports open on this, but they don't seem to work very well, at least in the FPGA world. I don't know what people may be using them in other areas, but especially when you do byte write enables and you end up with vectors, you end up actually with a whole bunch of different read mem h's wanting a byte each, and nothing seems to work right. So I don't know, there's some work to be done there, but at the moment I pulled the black box hook and the lever and got myself out of there. So at the moment I hide it all in my own bit of Verilog, but it would be nice to fix the language so we had a better way to kind of work directly with FPGA block ramps. Sometimes I'd overthink things. Really getting into this functional programming, life is great, and so I'd sit down, I'd come up with a fantastic algorithm, a completely functional algorithm looked great, and it turns out it was even more expensive when I ran it through synthesis than just doing the simple thing. So I think the important thing here is the bottom thing, having a closed loop where you could test something, try it out, and I definitely like using that with things like Yoast and XPNR. I can very quickly work out how fast it is, how expensive it is, all that kind of stuff. Some of the thoughts for the future. One of the first things I kind of came up against was a lot of my world is dealing with nibbles and bytes and words and all that kind of stuff. Wouldn't it be nice if the language had a few helpers for that? Scala had some nice ideas around implicit classes, which I'm using, which is quite good. I don't know if you know that's worth introducing into the language or into the utilities, but I quite like that. So counter with reset might have been useful at some stage. Some other things that you might need to use for building CPUs, like binary thermometer making masks, could be useful to put in the language. Rotates, and I've seen some bug reports on rotates. Okay, we need static rotates. We need dynamic rotates as well, because sometimes when you are implementing a barrel rotator, you need a barrel rotator. And so it'd be nice to have one there instead of maybe me guessing at what the best method to implement it might be. I talked to Scala a bit about partial bulk connections, and I don't know if that's touchy or not, but the ability to kind of, I got a bunch of these wires, and I want the left side wires to hook to the right side wires, and it's not a full connect, and it would just reduce. I got a bunch of boilerplate, just connecting units together, and it would probably reduce those quite a bunch. Constrained random testing, and I also started speaking to Scala about that. I've got my own set of test cases. You want some randomness, you want some edge conditions or edge cases, all that kind of stuff. It'd be nice to have more in the language where you have some support for that. And finally, maybe some FPGA-focused optimizations. In some cases, when we were playing on the VHDL side, we had a bit of a thought, well, I'm on a Xilinx Series 7, I've got 6 input LUTs, so this kind of algorithm or this layout would probably work best for it. Maybe, in the back end somewhere, it could be thinking about that so it knows the target. I don't know, we've talked about this a bit, but that could be quite useful where the back end optimizer knows what FPGA you're building for. Some of our next steps. So the idea on this core, and the same one with our VHDL core, was make it as simple as possible, get it functional, wrap it in a CI, and then start iterating. And that's kind of where we are. So it's functional, it works, it's got a set of test cases. I need to finally add Travis CI, but the idea will be every commit will run through a set of CI steps, and it's only at that point that we'll commit anything. And then it means we can start adding things relatively easy. Now we're functional. And it's like the software world. That's what we do. We get it functional, we wrap a CI, and we iterate. So there's a bunch we need to do. As I said, it's just functional. We'd like to add 32-bit support. That shouldn't be too difficult. We need to add, a decent interconnect. And I kind of punted on that because I wanted to do it properly. And I want to sit down with a few people and work out what the best way to build that interconnect might be. Things like caching and pipelining, all that kind of stuff. So come join us. There is actually a bunch of interesting Chisel challenges. We have a bunch of really interesting, maybe weird instructions on PowerPC. We have the rotate, let me get this right, rotate left, word, immediate, mask, insert instruction. We have population count, we have count leading zeros, we have count trailing zeros. We have a range of endianness, we have both. We don't have PDP endian, so I guess we have 2 of 3. And we have an EIEO instruction, so lots of interesting things to play with. Finally, if you're like me, you'll start collecting your FPGA. That's a small fraction of the FPGAs at IM, but you always seem to be gathering them over time. Thanks.
Okay. We have time for a question or two. Any questions? Sure. No questions. Come on. Okay. Thanks, Anton. Okay, cool. All right. Thank you.